Okay, so here we have another related rates problem, and here we're told that we have a 5-foot ladder leaning against a wall, and the base of the ladder is sliding away from the wall at a rate of 2 feet per second. And we're asked how fast is the top of the ladder sliding down the wall when the base of the ladder is 4 feet from the wall. Okay, so the first thing we want to do is draw a diagram. Right, so here we have our wall, there's the ground, and then we have a ladder. And we're told that the base of the ladder is sliding away from the wall, so we can picture it moving in that direction. And then what will happen as it moves away from the wall, since the ladder is a fixed length, necessarily it will have to slide down the wall, right? So we have these two things that are changing, and they're related to each other. Okay, so let's go ahead and label those two things that are changing. The first one is going to be the distance from the wall to the base of the ladder. And so we will label that one x. And remember, x is a function of time, but I'm going to just write it as x, and we just keep in our minds that it's changing over time. Okay? So x will be the distance from the wall to the foot of the ladder. Right, so that will be this quantity here on my diagram. That will be x, and then we'll use y for the height. So it's going to be this distance right here, and that is maybe all the way down. I labeled it h, huh? So we'll use y. Y is going to be the distance from the top of the ladder to the ground. Right, so those are the only two things that are changing. Notice that the length of the ladder is 5 feet, and that is not changing, so we do not assign a variable for that. Right, okay, but we will label that on our diagram, so that is going to be 5. Okay, so that is step 2. We've labeled all of our variables, and next we want to write down what we're given and what we want to solve for. So we are given in the problem that the base of the ladder is sliding away at a rate of 2 feet per second. So since x gives the distance from the wall to the foot of the ladder, that is going to mean that dx dt is equal to 2, right? Okay, and so that's the first piece of information. And then we're also told that, maybe I'll just underline, also told, so we care about the point in time when the base of the ladder is 4 feet from the wall. So that is, again, having to do with x, and this means that x is equal to 4. Okay, and then, so I wanted to label these. So these are the things that are given, right? So we'll write, we're given dx dt equals 2 and x equals 4, and we want, so we want to find how fast the top of the ladder is sliding down the wall, and that is how fast y is changing, so dy dt. Okay, so that's what we want to solve for. Now notice that we're we're often given information about when something is happening, but it's not in terms of exactly what point in time. We're not given like t equals 2 or something like that. So what happens is it's more convenient, it's definitely more convenient to use Leibniz notation instead of using the prime notation, and that's what I'm using here. You should definitely use this in these problems because using the other notation will just sort of cause confusion. It's not that convenient when it comes to this type of problem because we're not given an exact value of t. So this is just a lot more convenient. So I'll just, you should keep that in mind when you're doing these problems. Okay, so that is step 3. Now step 4, we want to find an equation that relates our variables. And this is one that will come up a lot in related rates problems. So since we assume that the wall is perpendicular to the ground, then we have a right triangle and we can use the Pythagorean theorem, right? So that would say that x squared plus y squared is equal to 25, right? Okay, and then so notice this is using geometry to find a formula that relates our two variables. Okay. In the next step, we differentiate, right? So we just differentiate this equation with respect to t. So maybe I'll write that out. So we're differentiating both sides with respect to t. Okay. So this is just really similar to how we've been doing implicit differentiation, but both of these variables are varying with respect to time. So we use the chain rule on both of them, right? So starting off here, we get 2x times dx dt, right? So the derivative of the outside function was that 2x, and then the derivative of the inside function, which is x, is dx dt. And then the same thing goes for y squared. It's actually exactly the same. We get 2y times dy dt. Okay? And then this is the derivative of a constant, so that is going to be 0 on the right-hand side. Now, what we do next is we want to plug in our known quantities, right? So we're given dx dt and x equals 4. Now, what we're not given, well, dy dt is what we want to solve for, so we expect that we're not given any information about that, but we don't know what y is going to be. And so this is a situation where we have to solve for what y is going to be when x is equal to 4, and then plug that in to our equation. So we need y. So what we're really asking is, what is y equal to when x equals 4, right? So the point in time that we care about, when x equals 4, what is y equal to? And we can just use our equation that relates those two variables. So this will always hold for any values of x and y. So we're going to use that in this case. So we get x squared plus y squared equals 25, right? So that means that y squared is equal to 25 minus x squared. And then it's going to be so y is going to be the square root of 25 minus x squared. Now, y is, well, technically when you solve this equation, you should get plus or minus the square root, but since we are, y represents a distance, we're not going to get a negative value in that case. So I'm just going to drop the plus or minus and just keep the positive value, and then plug in x equals 4 to get y. So 25 minus 4 squared is 25 minus 16, which you can check is 9, and then that will give us 3 for y. Okay, Now we're almost done. We now know what y is equal to. We have our values for dx dt and x equals 4, and we just plug all of those into this equation right here. So what we're doing now is plugging in 2 times x is equal to 4, dx dt is equal to 2, and then that y we just solved for is equal to 3, dy dt equals 0. And so solving this will, we will get dy dt equals, so this is 16, right? So we'll actually get negative 16 over 6, which simplifies to 8 over 3. Okay. So our units, let's check and see. So our units for dx dt were feet per second, so it's going to be the same thing for y. So negative 8/3 feet per second. And that is our answer. And notice that it is negative, and that makes sense because if we imagine the base of the ladder sliding out, we would imagine that y would be decreasing, and we know when the derivative of y is negative, then that thing is decreasing. So that's a good way of, checking your answer, if it makes sense. Okay, so we'll do another example in the next video.